In this video, we start to talk about correlation and covariance matrices of a random vector, which have lots of applications, and thus we look at the properties of correlation and covariance matrices. We look at some of the properties. If you have a random vector x equal to x1, x2, xn, then we define a correlation matrix and then a covariance matrix, and then we look at the properties of these. So correlation and covariance matrix are defined for a bunch of random variables. So let's say you have x1, x2, xn. Okay, so if I consider the correlation of x1 with itself, I put it here. Correlation of x1 with the last one, I put it here, and so on. So each entry of these matrix, so let's say if you consider correlation matrix Rxx, if I look at ith row and jth column, so I look at ith row and jth column, so I will have Rij, which is equal to mean of x of I, x of j. Okay. Basically, you could say that these Rxx, Rxx is equal to mean of this vector x if you write it in column, and then x transpose or conjugate, x transpose conjugate. Sometimes transpose conjugate we denote it by Hermitian. So we write it x Hermitian. That means that you transpose and conjugate the second one. So this gives you, the first one gives you a column vector. This gives you a row vector. If you multiply a column vector by a row vector, you will get a matrix. Okay, and this matrix, the first element is going to be x1, x1 conjugate. And the last one is x1, xn conjugate. Here you will get xn, x1 conjugate, and then you get xn, xn conjugate. And then you apply expected value over both of it. So you apply expected value over this matrix, and this expected value is applied on each individual of these terms, which is going to give you this correlation matrix. Similarly, you can form covariance matrix. The only difference is that you form the covariance matrix the same way that you form the correlation matrix. The only difference is that first you deduct from x1, you deduct mu x1, you remove the mean. From x2, you remove mu x2, etc. So all the random variables, you remove the mean, so you consider the deviation from the means, and then you apply the same operation, you get the covariance matrix. So the covariance matrix is the correlation matrix of your random vector when the means are already removed. If the means are 0, correlation matrix and covariance matrix, they are identical. So the ik entry of this guy is just the correlation of between the ith random variable and k random variable. Remember, if you have complex valued, you put a conjugate on the second one. Otherwise, the conjugation is not needed. So the ik entry of this matrix and ki entry, so let's say if you have an entry on upper diagonal and its symmetry here, they are equal. The only difference is that they have a conjugation on the other. So because you have to move the conjugate from this one on this one to get the other term. So it has a complex conjugate symmetry. So Rxx, from here I could say that Rxx is equal to Rxx complex conjugate and a Hermitian. So if I put a Hermitian here, remember that this Hermitian means transpose and conjugate. Okay. Similarly, the ij entry of this matrix is same as this one, just you need to remove the mean terms, and then you have the same property. So Cxx is equal to Cxx Hermitian. So the first property of here, what we have defined, we have defined the correlation matrix, we have defined the covariance matrix, and we have these two important properties. They are symmetrical. Obviously, from this definition, if I put X, remember that this transpose means that this X is like X1, X2, Xn. I wrote it like that because it takes less space. So this is the definition. So this definition and this definition are identical. The covariance matrix is equal to that. So you could quickly see that Cxx is equal to Rxx minus mu x Hermitian. And this Hermitian means complex conjugate. And other properties as well. So this is transpose, and Hermitian is equal to, you apply not only conjugate but also transpose. So this is abbreviation. So remember, in MATLAB, if you put a prime on the top of a vector, this will produce transpose and conjugate. But if you want to put just transpose, you have to put a prime and also a conjugate. So you see that it is easier in MATLAB to calculate Hermitian of a matrix or vector than its transpose and conjugate. This is because whenever in signal processing, whenever you deal with complex entities, if you transpose, automatically or most of the time, conjugate also is involved, and they are usually together.